Okay, so we're going to be doing stoichiometry. It's going to be at 3:05. Okay.
What time is it now? 3:20?
So let's see, how about we do it for octane?
Octane, okay.
Okay, so we're going to do C, okay, so C8, H, you know what? Let's do octanol. Okay, so C8, H18, O.
Okay, 1 oxygen.
Yep, that's
So-
octanol.
8 carbons.
So we're going to do that. And it's combustion reaction, so when we have combustion reaction, we always combine it with O2, and we're going to always have CO2 plus H2O. So that, whenever it says combustion,
You always add.
you're always going to have this last part. Always, whatever your fuel is.
So we have to combine everything, right?
Well, we got to balance everything.
Okay.
Now, is that, for instance, on the right-hand side of the arrow, is that an equals to, or is that?
Yeah,
it's going to-
basically.
Okay,
It yields, so it's
Okay.
going to produce that. But we need to balance it first.
I guess I was confused on that, alright.
Oh, so like a regular algebra equation balancing it? Like subtracting from.
Not like that.
I can't remember.
We want to balance. We want to put coefficients here, here, and here, so that everything on this side equals everything on that
Over
side.
there.
Maybe we even have to do one there. We'll see. We'll just
Alright.
do that just in case. So this is what I've seen is the easiest way to do it. Start with carbons, then go with hydrogens, and last step is oxygens, because here we have 2 sources of oxygen, whereas here we have 1 source of carbon, 1 source of hydrogen. So it's going to be a lot easier to figure out this one first. So let's say that we start off with 1 C8, H18O. If we have 1 C8, that means we have 8 Cs. Here's a source of 1 C, so
8.
we put the 8 there. Then we have 1 source of H18, so 18 H's, H2,
So 9.
so we're going to put a 9 there. Okay, now we're going to look at the O's. Okay, so we're going to take the O's to plug it in over here. So we have 8 O's there, or 8 O2's there, so we got 16,
16
and then we got 9 O's there
25.
for 25. Okay,
So we have 3 O's on that side, right?
that's right, we got that.
So
But
22.
here's just the source of 1 O. So we'll put 1 right there, meaning that we only really need to worry about 4 now. and 24.
So 22 O2. No, I'm sorry. Not 22.
12.
Yeah, 12. My bad.
There we go. So that's how you balance it out. And if that O wasn't there, we would have had to double the entire equation. We would have to put a 2 in front of that, 2 in front of that, I mean, 2 times that, 2 times that,
Yeah.
and then we would have had a whole number there that we could have used.
And now this was all with which topic? Stoichiometry?
Stoichiometry.
Stoichiometry?
So this is the first part,
Mm-hmm.
okay?
And balancing it.
Is balancing all of that. Now let's say that, okay, so I wanted to find out how much CO2 I would produce if I used a kilogram of fuel. Okay, 1 kilogram of fuel. And then later, I'm going to write this up here in the corner. I'm going to say that it is 89.2% yield. Okay? So I wanted to find out exactly how much CO2 I'm producing, because water, we need more, all the water we can get, right? But CO2, supposedly it's not good.
Right.
So, based on that, let's first find out what is the theoretical yield. This will help us to find the actual yield, but we want to find the theoretical yield.
Where did that 89.2 come from?
Yeah.
I just made it up.
Okay.
Okay.
So you want to, with that 89.2, that's like which you wanna,
So basically what we're gonna do is we're going to solve this all the way through,
okay.
and we're gonna figure out which is the theoretical yield of this. And the theoretical
Okay,
yield
okay.
is basically if 100% of this was used up. But the thing is that we know that gas, okay, this is octanol, is very close to gas. We know that it's not completely used up.
You can't use everything.
So there's going to be a little bit left, meaning that not all of that is going to be produced. Only 89.2% of whatever we get there is produced. So I want to find out
Oh,
how
okay,
much is produced.
Okay,
I got
that
you.
makes more sense.
So let's go ahead and do this. 1 kilogram of C8H18O, and O2, it comes from the atmosphere, so we're going to say it's an excess. Okay? Meaning that we don't have to worry about running out of O2.
Okay.
And we need to figure out how much CO2 is produced and how much H2O. Actually, you don't have to worry about H2O, we'll just worry about CO2.
Alright.
So, what's the first step?
It's a good question. Do you put, for instance, I think how he showed us is to put the entire CHO over, what would it be, 1 kilogram, I guess, in this instance?
Close.
You have to convert the
Let's
moles,
just
right?
do that. Exactly.
Oh, you have to
Convert it
look
to
for the
moles.
AMUs first?
Yeah.
Okay, so let's convert to moles. So we have 1,000 grams of C8H18O. Okay? So we want to convert this to moles, so we want moles on top, and we'll put grams on the bottom. How many grams per mole do we have of C8H18O?
How many grams of,
What's the molar mass of C8H18O?
we have to add that all up, right?
Yep. So you're going to do the C, so there's 8 times
8 times
C.
12.011.
Yep. And then we're going to do 18 times H, which is 1.008. And then we're going to do 1 times O, which is the 16. So 8 times 12, that's going to be 96.
Yeah.
96.08. And then we got that, so it's going to be about 18.144
16.144.
plus 16. So we add all that together.
130.22.
130.22. Okay, so now what we could actually do is that we can actually solve it for right there, or we can go straight to CO2, because we don't have to worry about a limiting reactant.
Okay.
Okay, so because this is actually, let's label this more clearly, 1 mole C8H18O. Because this is 1 mole of that, we can actually now convert it from moles of this to moles of that. Okay, so we got rid of our grams.
Right.
And now we're in moles. Let's do 1 mole of C8H18O on the bottom. And we want to do the equivalent of that in CO2. So this is 1, that is 8. 8 moles of CO2. Okay? Now let's say that I wanted to figure out how many grams, or how many kilograms. Let's see how many grams of CO2 I produce. Okay? I can add another step, because now I'm in moles of CO2. So I can go, I want to go into grams, I'll go for moles of CO2. So 1 mole of CO2 is equivalent to how many grams? C is 12,
12.
O is 16 each, so O times 2 is 32, 32 plus 12,
44.
44. So it's going to be about 44.01 grams. And that is how we get from 1 kilogram of octanol to how many grams we produce of CO2. And even then, if you want, you can convert it to kilograms
And now, where does the percentage play a factor in all this? You're 89.
after we get this.
Oh wow.
Yeah,
Okay.
I think it's.
You know what?
How long do they give us for that chemistry test?
Let's just do moles.
All right.
No, let's just do grams.
Okay. Well, we basically. Okay. Yeah. that
So
makes sense.
that divided by that times that times that.
Wait, why did he multiply straight across the top and then?
It works the same way.
Oh, does it really?
It's orders of operation.
Oh, that's crazy. Alright.
Multiplication and division, they take the same slot. They don't care who goes first. It all ends up the same. But yeah, you could just multiply that times that times that and divide by that.
Yeah, that's what I was doing.
You don't need parentheses.
Divided by 130.22. That'd be right. 2,703.
That's what I got. 2,000.
703.73.
So that's how many grams.
Grams.
So we do about 2.7 kilograms.
Kilograms, yeah.
Okay, so for every 1 kilogram of this we use, we release 2.7 kilograms
Of
Of that.
CO2.
theoretically.
Yeah.
So
That's actually helpful.
that's a lot more. I mean, that's like,
This is not how much we actually produce because we know we didn't use up all of that.
okay.
We only produced 89.2% of whatever we form. So what we do now is we take the 2.7 kilograms
Times 89%.
times the 89%, or we could do 0.892. And that is how much CO2 we actually produce.
2.4.
2.4 kilograms. Wow! That is a lot of CO2.
That is.
That I don't want to.
And that is a really long process. So just to kind of clarify once again, so we took the entire molecule itself,
Uh-huh,
and we said there was 1 kilogram of it.
exactly.
So basically that, we said 1,000 of the molecule, and then
1,000 grams.
1,000 grams.
1 kilogram, yeah.
And then after that, how did we get our next 130.22? I don't even remember anymore.
Okay, so
We
we
added up
converted to
the-
Added
moles.
up, yeah,
Oh,
we
right, the
converted
AMU of all of it.
So that's the AMU of that.
All right, and then we said 8 moles because we looked at carbon dioxide.
So
Alright.
there's 8 of those to every one of those.
Yeah.
And so we just did the conversion.
And then that very last one, the 44, we got
And
that
so-
was 1,
1 mole of CO2 is 44.01 grams.
it makes sense, wow.
So then, if we wanted to, we could see how much H2O we created too, right?
Exactly.
Just by switching out
I
the
mean,
8 moles.
all you need to do is just switch this number to 9
H2O, yeah.
and put 18 there,
That's cool.
and you actually will produce a lot more H2O. Well, you'll produce more moles of H2O, but less
Less kilograms.
kilograms because this is a 44 and the other one's just an 18.
That's interesting.
So it'd probably be about 1.5 kilograms.
So, can we do this process on Mars?
On Mars.
To create oxygen? Oh no, create water on Mars.
Yeah.
If you had a,
Well, you'd need oxygen first
Oh, yeah.
to do it.
We'd have to bring our own oxygen.
There's
So
a
it's
lot
not
of,
like I can create more from less,
yeah.
right?
can't create nothing. Something.
I mean, like Mars, it has plenty of carbon dioxide,
Yeah, it was like way too much.
but it doesn't have any water. Like if we were to take plants, it would be able to use the carbon dioxide, but it needs water.
Yeah.
So we would have to provide the water.